Cool, there we go. Yeah, so the general plan for today is to get the add working, right? So we're going to be able to add two numbers together in a CPU, which is probably what a CPU should be able to do anyways, right? Yeah, so that's the goal. The goal is to be able to add numbers together. Amazing. So let's get to work. So let's open up the CPU.v. And so what am I setting as the output right now? So because we were trying to figure out what we were doing. Output is the value we're trying to write. And yeah, I think what might be a good idea to just do a little bit of what's its name, debugging of this what we had last time, right? Is to effectively just have it go like iterations, right? So we're just gonna like test it out a little bit. You know what's probably a good idea? Let's get a visualizer. Verilog visualizer. Yes, convert Verilog. Ice. That's ah. Okay, cool. .u. Ah, there we go. Visual. Drop files here. Okay, cool. Let's actually uh, chip design. Let's just drop in all of the .v files. Open. Setup. Cool. And then CPU. How does this work? No, that's me downloading it. Run. IO instruction out. Okay, this is not. Oh, there we go. Here's the thing. We have instruction. We have clock, and we have it doing stuff. That's nice. There we go. So we have all of this going. We have the func 7 and stuff. We have our registers. And oh, there we go. We have a nice visualization of the compiled version of the thing. Amazing. Cool. So we have a nice visualization. I don't know why I cared about that. I'm going to be entirely real. I don't know why I cared about the visualization, but yeah. So we have that. And we just have to kind of keep going here. So, always. So when the clock goes to the positive edge. Hold on, let's pull up the Verilog. Verilog standard. Right, there we go. Pause edge. That does show up. Neg edge. Right, so we should do on the negative edge, we write the value. Yes, yes. So compile it, test it. So time 14 is when we're trying to write the thing out. Yes, yes. So we're trying to write back on finish. And so hold on. Let's just look at our registers. So we're gonna read on the positive edge. So on the positive edge, if it's this, we read it. Cool. And then we should write on the negative edge of the clock, just so it makes more sense. Cool. Then let's pull open the CPU, and then let's edit it so that now when we are outputting, we're not outputting the value right, we're outputting, let's say, val A. Right? Cool. So now I'll just put these all together. It's not actually outputting. Okay. CPU. Let's pull up on the test bench. Cool. So we're in the test bench here. We have instructions. They each 10 seconds, like 10 cycles in between them. And a clock just goes. Right? You know what? Let's change this to 20. 20, 20, 20, 20. Because I don't particularly care here. Stop is there. At time 4, the output was set to 0. Why is the output getting reset to empties at the end of our instructions? Oh, probably because we have no instruction going in. It's all zeros, right? That checks out. Cool. I should probably comment in what instruction this is. Hold on, now I have to rederive what instruction this is. Okay, so what is the opcode of this instruction? 110 010 110 010. add immediate. So it's an add immediate. Oh, so this is the add 15 to register 1. Hold on. Func 7. 1, 2, 3, 4, 5, 6, 7. The register, but 1, 2, 3, 4, 5, 6, 7. Oh, we're doing immediate format. Okay, hold on. 7, 8, 9, 10, 11, 12. Yep, we have the 12 bits for the immediate format. RS 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. RS 1. Func 3. And then the destination register. 1, 2, 3, 4, 5. Register 1. And then we are doing this. Yes. I should probably print out what register we're writing to in the yeah. Hold on. Nvim registers.v. Yeah. Cool. So, well, we can actually figure out what register we're writing to by printing out in cpu.v, right? So in our cpu.v, we can actually figure out what registers we're writing to. And so it's rs1 is what we want to be printing. So let's just print out rs1. No, we want to print out rd. Make sure we're actually writing to it. Yes, 1, 3, 2. That makes sense. Now we do rs1. It's 0, 2, 3. Yes, because it stays at 0. Because, yeah. Cool. Next. Oh, is it because we're permanently writing? It's probably because we're permanently writing. We should probably only set this to 1 when we're actually writing back. Yeah, that checks out. So I'll just throw that as... It's probably an instruction decode. Like, let's be entirely real here. It's probably instruction decode. That's issue. Well, no, we're just trying to write 0 to our thing originally, right? Yeah. Hold on. Out is rs1. What are we looking for? What are we looking for here? What we're looking for is probably something along the lines of no, we know RD. Let's print out func 7 and let's see. We are not getting any func 7s. CPU test bench. Hold on. CPU test bench. Because we're not doing any func 7s, I don't think. Yeah, we're not doing any func 7s. Let's print out the immediate value. We already know we're trying to write it. Func 3 is going to be 0 for us here. Okay, hold on. Add I. And we're adding immediate to... Where is add I? Add I. We're adding immediate to RS... Hold on. So it goes from... RS1 is x1. No, x0. Comma, immediate 15. And we're adding it into x1. This one is add x1, x2. Stored into x3, I believe. And this one is... Hold on. It's another add. I don't particularly care. We're just trying to get the x3 value to be good. Yeah, just the val right. We want the val right to be good here, right? So, yeah. Amazing. So, what we're going to do here at this point is we're just going to continue changing it, modifying it, you know? So, how are we going to do that? This I do not know, per se, right? So, yeah. So, how are we going to get it to do that? Okay, let's pull up the CPU. Let's actually look at what exactly we're doing. So, we know the information going into... What? Maybe... Let's go into the registers. Let's go into the registers. Write enable. Maybe we shouldn't do write enable for everything. But for all 3 of the ones we're doing, we should do write enable. Hold on, hear me out. What if I do write enable is just this part of the opcode, right? So the last bit of the opcode, like the 0th bit of the opcode. That might be nice. Hold on. But maybe we're like breaking it, right? So write enable is, I'm just gonna say it as opcode of 0. Cool. it's let's get it to print out a very nice opcode of 0, right? Well, let's have it print out the opcode. 0, 13, 33. Does that check out with test bench? These numbers should be way bigger than that. So I think that's what our issue is. I am bad at writing the binary here. I also don't want to convert this into decimals. So, oh wait, we're not trying to print out the opcode. Hold on. No. We have to print out the instruction. Yeah. Whoops. Whoopsies. Instruction. But the opcode going from 0 to 13 and then 33 makes no sense. Because it should be at 3 plus like 4, 8, 16 plus 32. It should be like 40 something. It should not be at 13. That probably explains why there's no ads going on. Also the add immediate. We should have like a nice opcode there. Hold on. Instruction decode. We are feeding it. We are expecting that we get an opcode out of it. Hold on. Opcode. It's instruction of 6:0. Yeah, that should be correct. And this happens on the positive edge of the clock. I'll have this all go on the negative edge on the clock. Let's see if that works. That is a big number. Yes, that's a very big number. Okay. I'll set all of these to also update at the same time. Negative edge, negative edge. Negative edge of the clock. Okay, these numbers are... Oh, that's probably the full instruction. Hold on. Let's print out... Yeah, that's the full instruction. Let's print out the opcode. 0, 13, 33. How is it getting... Oh, wait. These are... The first one's 0, then it's 13, 33, and it doesn't change. Yes. This checks out. This all checks out. This makes a lot of sense, actually. Hello there, Mr. David JYLU7. Good afternoon indeed to you, too. How are you doing this fine day? But yeah, so we're gonna... that's good. Doing great is always a great thing, you know? Hey, that's good. Hope you had a good exercise. You know how it is. Hope you had an amazing exercise. Nice. Hope they taste good. Yeah. Hold on. If that turns out to be the issue, I will be kind of annoyed. Yeah, let's print out the val right here. We're writing 15 to it. So that's the first instruction. We're telling it to write 15. Then in the next instruction at 46, we're not putting any information there. Okay. Now let's figure out what's being sent into the actual CPU. So yeah. 0, 15, 0. Okay, I want to be able to read the nvim registers.v. And so here, let me just like monitor always at pause edge clock. Well, let me just copy the code. Let me just copy the code from the test bench. Let me just yoink that in and paste it down here. At time this, I'll say x1, and I'll just set it as the values of x1. compile and run. Cool. So x1 is 0, and then we just set it to f. This is a good sign. It's not changing from what we expected to change. So the x1 is there. Hold on, I should... Can I type on keyboard? Cool. CPU test bench. Cool. So let's go back in here and let's figure out what's going on here. So x1 is 15. This is correct. x2. Okay, so let me actually rebuild this instruction from the ground up. So our opcode is, we know it's here, right? So there's our opcode. Next, destination register. It's 3. We're moving into x3. Cool. Then we have func3. 1, 2, 3. It's all zeros, so we know that's add, right? Cool. So now that we know it's add, we have rs1 and rs2, right? So 1, 2, 3, 4, 5. So rs2 is x2. 1, 2, 3, 4, 5. rs1 is x1. Cool. So let's go in here and let's paste this down here, and let's print out what the value in R3 is. Sorry, X3. Not R3, X3. It's cool. So X3 is getting written to with a 0. There's a problem, I think. Is our adder not adding? Hold on. NVIM. Well, let's go into registers. Let me yoink the monitor line. Cool. NVIM ALU. Cool. So let's go in here. And so if we expect... Hold on. Always at pause edge of the clock, on the positive edge, if func7 is 0, now let's just monitor func7. Let's just monitor func7. Let's see if we're actually adding. Func7 here. Func7. Func7. We're just doing all of these print statements. Func7, it's always 0. Right? Yeah, it's always 0. We know it's always 0. Cool. So we know func7 is 0. So let's just print out. What is the output here? I should probably print out input data A and B, but, you know, that's for a little bit of time. Output. I have it labeled here as func7. We are printing out F for a little bit. And then we are not having any output, right? So this makes a little bit of sense. This actually makes a little bit of sense, right? So, I should probably also change stream title. Hold on. Give me a second. Let me make this accurate. Designing CPU. Today we make it add numbers. Cool. I'm editing stream title because that's actually kind of important. Cool. There we go. And so now we have ALU dot... So our ALU is outputting. Right? So that's the output of our ALU. Cool. I'm commenting this out. So our ALU works as intended. I mean, it's simple enough that it's like, if it doesn't, you know, it's cooked, right? Cool. So the output of the ALU is val write. Let's just print out val write. Not print out, always do that. Cool. Then what I have to do is nvim CPU test bench of, and let's just always not initial, always at time t. At time t, and I will just print out because I want to see always process not have delay, infinite loop. That checks out. Yes, sir. Iterate every second. Cool. There we go. I'm going to edit the registers because I don't want to print out the state of every register right now. I will comment this stuff out as you do. I should probably just yank those characters, but like whatever, this is fast enough, you know? Cool. So output goes 0, because we're trying to do 0 stuff here. And then it goes to 15. Yes, this is correct. Val right is set to 15. Okay. So we are trying to write 15 to our registers. Right? So registers, we do have val right. Let's output opcode of 0. Opcode of 0. It's just like permanently 1. Well, it starts at 0, but it's permanently 1 over here. So we're trying to send the right stuff into our registers. Right? So we have write back is enabled. We have val write is done. Let's print out RD. Right? Let's make sure we're trying to write to the right thing. We are trying to write to register 1, then 3, then 2. This checks out. Right? So this all checks out. So we are writing to register 1. Like, that works. The problem is we're not able to write to register 3. Cool. Hold on, let me edit. Let me like comment this. Y2J. Let me comment this out and have this printing be in the CPU, so that we can just print out multiple things. So always on the negative edge of the clock. Time. So we're going to print out not out. We're going to print out RD. 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 So that's the register we're trying to write to. I'll paste that in here. I'll add a space here just so it looks nice. Cool. So we have this, and then we're just gonna paste one down here. And we're gonna do opcode of 0 is what we're looking for here. Val right probably. Val right. So destination register. Val right. Val right. Let's run this. Okay, cool. So we have it. Val right is 0 here. We're not writing anything. 0, we're trying to write there. 15, we're trying to write there. Yeah, we're trying to write 15 there. Cool. Then here, what happened is we're trying to write 15 to... no, we're not trying to write 15 to 3. Well, val right stays as 15, so that's whatever. Right, so that is what it is. And then RD is... it changes. So val right is correct. RD is correct. We're currently trying to write to the right spot. So let's go. So the problem's not the ALU. The problem is not the ALU. The problem is registers. And for our registers do this on the negative edge. Yeah, that's whatever. If write enable. Huh. Wait. I'll do this on negative edge. If write enable, then print out write enabled. Write enabled. I'll just do write enable. I'll just print out write enable. Enable. And this is from the register side, right? So write enable. Cool. Unable to bind to it. I mean, it's a wire. What is the problem? Line 18. Did I spell it wrong? Oh, it's write underscore enable. Whoopsies. Whoopsies. That's how we call it in the upper layer. The whoopsies indeed. Cool. So write enable is 1. We are trying to write to register to already 1. Why are we stop printing RD here from here? Okay, whatever. Okay, cool. So why are we unable to write back here? This is a very good question that I do not know the answer to. But we're going to figure that out. So wipe that. Invims. Cool. I think the problem is with there. At negative edge. Try to tell us what we're writing. Yeah. Hold on. Let's continue to print out T3 and let's stop printing out this because we know, as I think, we're feeding in the right stuff to the CPU, right? So what is going on here? X3 does get set to 15 by the very end here, right? Because remember, 0 to 20 is like nothing burger. 21 to 40 is like the adding circuit. And then here's when we actually write it, and then it goes blank. Probably because our write enable is on, and our destination is still 3. Yes. Yeah, that checks out. So we need to turn off write enable, like, very quickly. Like, it should be off, like, within, like, 1 or 2. Right? Or alternatively, we know it happens over 4, so let's just make the clock go faster. Yes? Yes. CPU testbench.v. Yes. Okay. The instruction, we know it goes over 4, so I'll just have this go for 5. And we're going to cheat this. X3 is 15, and they get set to blank. Why does it get set to blank? Because here is where we set X1, then we set X3, and then X3 is blank. Why is X3 blank? What tells X3 to go blank? Let's look at what's in X2. X2 is permanently blank. That probably explains it. Because we're trying to do stuff with thing. So I have to, by default, set these guys to 0. Yeah. I have, like, initialize them with something. I'll initialize them with 1. It's not taking in the initialization. This is not great, but whatever. So then, if that's not taking in initialization, let's just paste this in twice more, and we just have it go. We just do this, X2, X3, and I don't know, let's set the immediate to different numbers. Let's set this to be 31, and this to be, whatever, that one's 11, right? I don't know. Well, I mean, we're going to overwrite it, but whatever. Compile and test. X2 gets set to blank very quickly. Then when it's, okay, hold on. 15, 31, 46. Okay. 15 plus 31 is probably 46. Why is X2... Hold on. Let's just keep reading out the register values. Let's print out X1 as well. Obviously, we know X0 is always 0, right? So, like, whatever. And print out X3. Cool. Why is it not printing out X2? Let me do that. Requires system verilog. But why is the first one working? Huh? Huh? Okay, that's strange. Yeah, very strange. X2, we're printing out X2. Okay, you know what? X1 is this, comma, X2 equals %sign H, %sign 0D, comma, X3 equals %sign H, percent sign 0D, x1, x1, x2, x2, x3, x3. Cool. Cool, so we have all the stuff. So x1 gets written to 15, right? So 1 to 5 is blank time. Then 6 to 10 is we're trying to write to here. Then we're also writing 15 to x2. Sorry, no, we're writing 31 to x2. And then we're writing 11 to x3, so it takes a little bit to update. Right, so there's correct. Then we are just moving x1 into x3. We're adding it to 0. Right, then what? Then we're... What is going on here? Hold on. Let me go into the CPU test bench, and let me just like have this run for longer. Like, let's be real. Let me have the final stop. I don't know, let's have these run for 6 cycles each. Okay, so hold on. What are our instructions again? What is the last one especially? I have to rediscover what this last one does. Cool. So, last one, opcode. Yep, matches. Next, the destination register. 1, 2, 3, 4, 5. Destination is x2. So we're going into x2. Yep. 1, 2, 3, 4, 5. Cool. Func3 is 0. 0, yep. RS1, 1, 2, 3, 4, 5 is x3. Yep. x3. Cool. And then dang. Then x1 is the other one. 1, 2, 3, 4, 5. Yep. And 0. So it's x1, and then this is just an add. Cool. So we're adding x3, x1 to get to x2, and this is adding x1, x2 to get x3. Cool. So adding these two to get to 46. Yeah, hold on. 15 plus 31 is 46. Yeah, that checks out. Hold on. Let me just print out will begin, then $monitor, and I will just print out a dash line. I will just do that. Extra digits given for binary line 9? Huh? Oh, I forgot the semicolons. Whoopsies. Cool. So this is our starting time, right? So we all set this. Well, x3 gets it. I understand why it's not initialized. Finish. Nvim. Hold on. Nvim. Registers.v. I don't know how to initialize them all together, so I'll just set equals 0, equals 0, equals 0. Cool. There we go. So they're all set to 0. Then what we do is we're writing 15 to x1. Yep. Then what we do is we are writing 31 to x2. That's taking a little bit to propagate. Then we're writing 11 to x3, taking a little bit to propagate. Then what we're doing is we're writing x1 plus x2 to x3. No, that feels wrong though, because this number is like wrong. So that's like an issue. Unfortunate. And then we're like overwriting all of this, huh? Let's go into registers and let's like print some more stuff out. Let's print out the out W. Out A, out B. We're not using out W. We want data W. Data W equals percent sign H, percent sign 0D. comma, data W, comma, data W. Malform statement. How is this a malform statement? Line 16, right? 17. X1, X1, X2, X2, X3, X3. Hold on, if I just replace this with X1, X1. That works. No. I understand it now. We need a comma here, because that's a parameter to it. That makes sense. This makes a lot of sense. Cool, so. Oh, it's because it's looping back. Okay, so it's going too fast. So let's go back to the CPU test bench. So we can see it's taking like 2 cycles-ish. So let's, I don't know, let's set it to 4. Cool. So what are we getting here? That's the correct final output. It's just what happened to our value in x3. Wait, no, hold on. 0. Yeah. Then we're writing 15. Here, we're going to go and write. No, the first instruction is to write 15. Then by this time, 15 has been written. So that timing is like perfect. Right? Then we are writing 31 in here. So that timing is also perfect. Then writing 11 in here. Yep, that's perfect. 15, 31, 11. Cool. Next, we're writing 15 into... What? Okay, hold on. What is going on here? We're trying to write 46. Because... Hold on. Isn't the instruction... We're writing into x2. x1, x3 are here. 46. How are we getting 46? How are we getting 46? Hold on. What are our instructions here? We should be getting like 30 in x2. But we're actually getting x2 plus whatever. Which is wrong. Hold on. Let's recalculate this. Let's go back here. So destination is x2. This is correct. 1, 2, 3, 4, 5. Destination is in fact x2. Then after that we have func3, which are all zeros. Then we have x3 as rs1. 1, 2, 3, 4, 5. And x1 as rs1. 1, 2, 3, 4, 5. Cool. And then yeah, 1, 2, 3, 4, 5, 6, 7 for func7, which is 0 in this instance. Okay. Cool. How is this failing? That's a very interesting question. Yeah. Okay. Cool. How is that a thing? So we have the instruction, right? So it's going very peacefully, very nicely. It's having a great time. This is in fact correct. Are we feeding the wrong RS1, RS2, and destination register into our registers? This is a good thing to check. Let's data W, whatever. I don't particularly care about data W. Let's see what reg A is. No, let's see. Yeah, no, we're writing to the right register. That's fine. Reg A. Reg A. Reg A. So reg A. Yeah, input 0. We're pulling out 0, because we're just writing into that. Then we're pulling out 2, and we're pulling out data from 3. Yes. So this is just a time for the final one to settle, right? So we know that. So we're pulling out data from 3. And so we have the F, yeah. So pulling out 15, right? So then let's have this be reg B. We should also be pulling out 15 here. We are in fact, yeah, we're pulling out register 1, yeah, which is 15, yep. How are we getting to 46? Right? So go into the ALU. Let's print out the output time. Why is the ALU outputting 46 here? What is making it output 46? Func7 is 0. I'll have this run on the negative edge of the clock. Cool. So, output should be 15 plus 15 is not 46. Hold on. Let's get the values. What is in the value of input data A? Input data A and input data B, and let's also, well, A, and then let's also just print out input data B and input data B. And so here I'll put like in A, comma, in B equals human readable number and %0D, and let's see what the output is. Cool. Well, why is input A 31? Why is it reading from X2 here? Where reg A is the problem. Let's pull open registers. Let's print out reg A. Let's print out reg A, and let's figure out why this is having issues, right? Cool. Reg A is 3. Hold on. Let's have the end run for longer. So instead of 4, let's have the end run for 10. I don't know. Cool. It does settle down to 30. Why? Takes a second. It goes up to 46 and settles down to 30. Cool. I think the problem here is that I am using registers, but I should be using wires. So let's go back into our instruction decode.v and let's figure out, and let's get this to use wires, not registers. Wire for clock. Why are all of these registers? These should be wires. Output should be wires. Opcode is not declared a valid L value in this. Okay. You know what? You know what we're going to do here? We're going to take this and we'll ask an AI assistant. And let's see what the AI assistant will tell us to do. And we'll add in upload file. Let's add in our instruction decode. Okay, well, let's copy our instruction decode. How do I have this module just be splitting up the input, and it should not add a whole clock cycle of delay? Now let's see if this actually understands what I'm trying to do, or if it's just stupid. Let's see if it understands. Why? Yeah, you use combinational logic instead of sequential logic. Output wire. Remove clock. Oh yes. This should not be taking clock as an input. Well, I'll keep it as an input. Just, ignore it. Whatever. Oh, output's already declared as wire. Ah. Ah, I see. Well then, just use a sign. Ah. I see. Cool. Well, let me just, I'm gonna delete the clock references. And I'm just gonna set this to a sign, and then hopefully this will work. Sign ln should be equal, not the pointed into arrow. Yes, this is correct. I do want to use combinational logic. I just did not understand how Verilog worked. I assumed it would be very smart. It is clearly not. The ops came for me and they failed, you know? Cool. Wrong number of ports, yes, okay. Hold on, instruction decode, we're gonna remove the clock. This is not gonna be pipelined CPU yet, okay? Cool. It's wrong. In A, in B, 15-0. Okay. Why is it failing to write to that? Okay, cool. So let's, we're not printing anything out here. We probably should, though. Always. On the negative edge of the clock, we are going to print out the, we're going to print out RD. Yeah, this is correct. Yes. RD is 2, 3. RD is 1. Finish. Yeah, okay, so we should have the lines there. Not registers. The ALU we know is reliable, so I'm just gonna comment this out. And we're doing this on the negative edge of the clock. As you do. Cool, so here we are. So why is x1 just permanently set to 0? So we're correctly writing 15 and 31 here, right? So that's... Is it supposed to be 15 for x2? And 31 for x3? No, that feels wrong. RD is in fact 1, that is correct. Right? Yeah. Cool, so we have all of that. Okay. So what we have to do here is we have x1. So from here we hold on. This is not the problem. We know this isn't the problem because the output is correct. Let's go down here and RD is correct. Okay, hold on. Is val right correct? Val right, and let's do it here as well. So the value we're actually physically writing into it. Yeah. Alright, cool. I should probably rename that because I'm going to get confused. It's at time t. Val right is that. Cool. So, val right, we're writing 0 here, 0 here, 15 here. Is it just delayed? Hold on. Let me give it more time here. So instead of 4, I'll set this to 10. We will see how it goes as it just propagates via the clock. I've built a pseudo pipeline CPU, which is bad, but you know, we'll see. Cool. So first 10 is nonsense doo-doo, we don't care. The next 10, yep, we write that 15 in x1. We write 15 we write 31 in x2. We write 11 x3. Yeah, checks out. It's just taking a while. Yeah. 11. Then we just move. Then we add these two to get to 46 in x3. And then for the last 10, 15 plus 46 is 61. Okay. This all checks out. The math checks out. It's actually we're able to add numbers together. It's good. So we have a very long delay here. Yeah. Cool. Let me bring my nice lines back. Very helpful print debugging. Cool, there's the lines. Cool. 0, 0, 0, 15. So it looks like it takes like I don't know, 4 cycles for it to fix itself. So, but we know 4 is excessive. So let's have it do it 6 consistently. Yes. Let's have it go. Oh, hold on. CPU test bench. Let's have it instead of 10. Let's do it 6, and let's figure out how to make this time shorter by using wires and combinational logic more instead of whatever nonsense I was doing there. Cool. Now it's shorter. 46. Is that correct? 31. Hold on. 15, 31, 11. 15 plus 31. This is wrong. Yeah, it should be 15 plus 31, which is bigger. So hold on. Let's set this to... Let's set this all to a nice 8. Oh, probably because we're skipping the end by doing this. Yeah. Yeah, okay, so 61 is correct. Yeah, we are doing some skippage here. Whatever. It is what it is. Cool. So, what we have to do here is we have to combine this all together into one. So, how are we going to do add? We're going to do add by taking... okay. What is the delay here? Let's actually find out what the delay is here. Is it in right back? Because we should just be able to do like pause edge, pause edge. This I'm going to set to pause edge as well, because there's no reason this should be on neg edge. Cool. So 61. That's taking slower. So I'll have this on the negative edge. So we read on the positive edge, we write on the negative edge. Let's go to the ALU. The ALU does everything on the positive edge. Let's have the ALU do everything on the negative edge. And then let's go down here and let's write on the positive edge. So when we do our ALU stuff, it should be faster. And we're no longer ALU bound. Yes. Hold on. 0, 0, 0 took like 2 cycles. Here it took like 2 cycles. 2 cycles. Well, not 2, it's like 4. Whatever. Here it took 4. It updates very quickly. Here it took like 6. Why does this take longer? This is a question. Hold on, can I combine these two? Invalid. Okay. These shouldn't be on the clock. Only write should be on the clock. I think the moment the input updates, this output should update like instantly. Yes. So out A and out B, because they're there. So I'm just gonna comment out this line because we don't use out W, and then I'm gonna do assign. I'll have reg B do whatever it's doing now. And this will complain about syntax errors, but that's fine. We're just trying to get it to do combinational logic, right? Because we're big combinational logic fans out here. We do not like sequential logic. We are combinational logic, massive giga fans, if you will, you know? So assign. Let's just edit out A for this, and let's see what the syntax errors here look like. Cool. Unable to bind reg A. Why? Because out A. Unable to bind reg A. Reg A is input, right? Yes, reg A is in fact input. Oh, hold on. We should like manually mux this. Out A equals. Let's just have this be a ternary. Reg A is 0 question mark 0 colon. And I'll just have it as like effectively I'm building a mux. 0 colon, and then here we have reg A reg A equals 1, question mark, x1, colon, and then we're just effectively having a switch statement here. Reg A equals 2, question mark, x2, colon, reg A is 3, question mark, x3, semicolon. Cool. And I'll just delete this. Syntax error on line 18, which is this one. Cool. 0. Let's comment that out and let's just set this to 1. It's either 0 or 1. Invalid modular item in line 20. Oh, probably because no semicolon. Probably a useful thing to have. Out B is not a valid L value. Cool. Now, let me set this to x1. Still not a bad value. Okay, cool. So then, what I'm going to do now then is just giga parentheses, yes? Yes, giga parentheses. And then, so we have this one as the big parentheses. This one is that parentheses. And then I need one more parentheses over this last statement. Syntax error in 18. Syntax error in continuous assignment. Parentheses is correct. Parentheses is correct. Parentheses is correct. Parentheses is correct. Oh, I need a colon here. Otherwise, it's 0. Whoops. There we go. And let's see if I actually need all these parentheses. 1, 2, 3. Delete. 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 And so that's just a fallback. Yeah, there we go. Cool. So I'm just gonna yoink that in there. And so this is just theoretically going to make it faster. Out A, this is going to be, I'm just going to replace all of the A's here with B, right? Because this is exactly what we need. Reg A, reg B, reg B. Cool. There we go. It feels just instinctively much faster. Right? Cool. Amazing. Hold on, let me... Because what actually matters is like the register times, right? So this is going to be the negative edge. Cool, now we're printing out at all timestamps. It's just the problem here is we're not getting our nice lines. I would like my nice lines, you know? Cool. So here we are. 1, 3, 5, 7. It's changing much quicker. Now, cool. So, instruction coming in should be a wire. It's an input, it's a wire. Cool. So all of these ones are wires, so there's 0 delay on those. There's also 0 delay from that to getting the stuff from the registers, right? So this is good. This is a very good sign. Then from here, ALU needs delay, so I should have that change on the positive edge and then rewrite on the negative edge, theoretically. Right? So we write on the negative edge. And the ALU we have going on the positive edge. There we go. How fast are we here? Here we... Hold on, is it slower? So by 11 and 15 is written here. Here, by 12 it's written. Yes, because it delays a little extra bit. Because we're writing on the positive edge. Because 10 is our line. Remember, 10 is our line. So 11, how are we written here by 11? That's very fast. Oh, because we're just writing immediate value. We're not relying on ALU. 41, 43. 41, 44. This is delayed it by 1. Okay, hold on. What if I... Hold on. Hold on. NVIM, lobby. Well, so not CPU, CPU test bench. Hold on, I'll just like print it out. Here, I'll just print out clock. CLK equals, and then I'll do %sign H, comma CLK. What is the clock here? What? So odd numbers are it's on, even number it's off. Cool. So at 10 it's off, right? So we change it and it's off. Then at 11 it turns back on. So because it turns back on at 11, we should on the rising edge. So for 11, we should have the ALU run. Then on the falling edge, we're writing back here, which is exactly what happens, right? Yes. Cool. And so I'll just make this clock speed like a little bit faster, right? CPU test bench. And let's have the clock speed be just a little tiny bit faster. So instead of, not clock speed, the time we're giving it here. Let's have this go for 4. 4, 4, 4, 4, 4, 4. Cool. It's failing. We're failing to write the 15 at the start properly. They're all 101, correct? Yes. I'll just have a parameter. Parameter time is 4. Not time. Time. Yes, all caps. Because I don't want to change it in all the spots all the time, right? So time. Okay, cool. So 4 is too small. Set 6. 6 leads to 61, which is the correct answer. Why is it a little bit unstable here? So hold on. Why does the 15 take so long to write? So 1, 2, 3, 4, 5. So 0, nothing happens. 1, 2, 3, 4, 5. On 6, we get our new instruction. And then 7, 8, 9, 10 it updates. So it takes 4 to update. And then obviously we were doing issues there. 1, 2, 3, 4 to update. 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 It takes 4 cycles to fully update. Not 4 cycles, it's like 2 cycles of the clock, right? So if it's like a 2 GHz processor, we're doing 1 billion instructions per second. So we have a CPI of 0.5 right now. I don't fully care about that. I just want to get this a little bit faster. Yeah, cool. And then CPU.v. This should be wires. In A should be wires. That's the problem. Yes. So out should be a wire, not a register. So it's assign out is RD. Assign out is RD. And in A, I will assign it. And in A should be a wire. Cool. So compiles, it runs, and way faster. Look at that. Change, rising, falling, it's in. It works flawlessly. This is amazing. So the clock goes 1, and then by the time it goes back to 0, it's locked in, information is back, ready to go. So hold on. NVIM CPU test bench. And so let's set the time here to 2, and let's see what breaks. It does fail to do that, probably because of duplicate time nonsense. So let's set this to 4. 61, perfect. That's really good. That's really nice. We have it doing basic add ops. And so this is a great success. We've met that goal. And so now we have to edit it. And we have to modify it to build the framework and get it to run the add ops. Get it to run arithmetic operations. This is what we want to do. We want to run arithmetic operations. I'll write the full word. operations. Cool. Massive amount of text there. My bad. My bad for that. But this is fine, actually. Because now we extend it, right? So we have this, right? And so, hold on. Let me see what happens if I just add text to just like numbers themselves again. Right, because we're not changing the inputs, right? Hold on. Let me... Cool. So, yoink this, paste it in, and so let's add x2, x2, and x2 to itself. 107. 61 plus 46 is 107. This is correct. Cool. And so we can add a thing to itself, which is a very nice sign. Very good. Big fan. Yes. Now we just have to, let's implement, I don't know, let's implement subtraction. Yeah, let's implement subtraction. So subtraction requires a different func7. It should already be implemented in our ALU. So I just have to edit the func7 for one of these ops. So I don't know, I'll set this as subtract x2 minus x1 and put that into, let's put into x3. For the fun of it, let's just change this up. Right? So, subtraction. 1 1 0 0 1 1 0. Yep. Next, destination register. 3 1 2 3 4 5. Cool. Next up, func3 0 1 2 3. Next up, rs1. rs1 should be x2. Boom. 1 2 3 4 5. rs2. rs2 should be x1 instead of 2. Cool. 3 4 5. And then func7 should be 16. Not 16. That's 32. So that's 1 2 3 4. So that's the first one. 1 2. Cool. So that should be 32. Yes. And so let's see if that works. 92. There we go. So that's 107 minus 15. That's 92. Yes, that's correct. So we have subtraction working. Cool. Now let's just go down the list and implement all of these. XOR. Yes, let's do XOR. Let's just implement a whole bunch of stuff. Else if. Yes, this should probably be combinatoric logic. Yeah, this should probably be combinatoric logic, actually. Not whatever nonsense I'm doing here. But whatever, I don't actually... Oh, I'm entirely real. I don't want to put that much effort into fixing this now, so we will dig our grave a little bit deeper, and then we'll fix it, you know? Func3 is... So for XOR is 4, so func3 is 4. Because, okay, I'm just gonna... that's actually a bad check for func7. Yeah, okay, hold on. If func3 is 0, then we'll have sub-ifs. If func7 is 0, do this, otherwise do that. Else if func3 is 4, out is equal to input data A plus input data B, not plus, it's XOR, caret. Cool. And let's also implement OR. No. Cool. So OR is 6. It's a pipe. So we have XOR, OR, let's do AND. So AND is 7. And it's an ampersand. Cool. Then left shift, right shift is 1 5. I will not be doing any of the shifts just yet because those arithmetic extension and whatnot. Yeah, because I had to set up 0 extension. But this should just work. So we have XOR and XOR or an AND. So let's just use those instructions, shall we? Paste, paste. So this should be XOR. And XOR has a func 3e. So XOR has a func 7 of 0. And a func 3, 1, 2, okay, 1, 2, 3, 4, 5. Func 3 for XOR is 4, so 1, 0, 0. And for OR, it's 6, so it's 1, 1, 0. Paste. Cool. And for AND, it's 1, 1, 1, because 7. Cool. So I should probably rename this XOR, OR, AND. Cool. Syntax error in ALU 22, 24, 26, and 27. NVIM ALU 22. Oh, it's all my refusal to use semicolons. There we go. Cool. So, this ain't binary. Let me NVIM registers of V, because the registers are where the data actually is. So instead of hex, let's do binary for this, 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 and regular. I don't actually particularly care about the value. Cool. So there we go. That's very big. ALU.v. Okay, that's unfortunate. This is fine, actually. So let's look at the I should name the thing that's happening. Hold on. CPU testament. I should name this stuff. There's a lot of instructions though. Also, this isn't 15. This is 31, and this is 11. Yeah, okay, whatever. I'll leave it in the comment. Whatever. I know what it is. XOR and or an AND. XOR. Yeah, that looks visually about right. No, it doesn't. You should have a nice 1, 1, 0 here. No, that 0 should be a 1. No, that 0 should be a 0. We should have a nice 1, 1, 0, 0, 1. Oh, wait, no, it's up here. Whoops. 1, 0, 1, 1, 1, 0. Yeah, that looks... Is that right? Hold on. 92, 92, 92. Oh my god. NVIM CPU .v. What am I saying? It's opcode of 0. The problem is... No, opcodes should be 0. They should all be ending with 1. Right? Yeah, they're all ending with a 1, so we're fine there. Yeah. Obviously, looking at that, we will fix that later. That's a later type of fix, right? But... Okay. Cool. You know, this is to be a tweet. Just got my RISC-V CPU design to be able to do ads and subs. That's a tweet. I'm gonna scroll up a whole bunch here to try to get to here. And I'm taking a screenshot of this. Commenting it there. Probably not useful to literally anybody, but whatever. Yeah. Cool. So, I think... yeah, I think we keep going here. Oh my god. Come on, guys. Like... Let me report this. Hold on, let me report the messages. Spam, scams, bots, advertising, reviewers service. It's bad. submit that report, block this user, close, cool. And then how do I delete this message? Whatever, that'll just stay there, and I'm gonna refresh this. Cool, there we go. We're back. We do chat moderation here, you know? We moderate our chat, so it's a very nice, healthy chat, you know? Cool. Amazing. So, we keep going. We keep, yeah, we keep going. We have a CPU, and we're using combinational logic because I love combinational logic. It's my favorite type of logic, you know? Yeah. I should probably actually use combinational logic in the, You know what? We're gonna do it. We're gonna use combinational logic in the... No, we're not. We're not gonna use combinational logic in the ALU. No, that was a lie. That was a big fat lie for me. We're gonna fix this. Func3 is that. That is that. If it's that, it's that. If it's that, it's that. Else out is 0. Yeah, it checks out. Okay, this should just work. Hold on. Let me check this out. Yeah. Okay, so let's just run it. Okay, last one is OR. So we should expect to see 1, 1, 0, and then 1, 1, 1, 1. Because 15 and 107 is just going to be plus 107 plus 4, so that's be 1, 1, 1. 92, 92, 92. It's not writing back. Why? Oh my god. Problem is sequential logic. I think the problem here is sequential logic. So let me set the combinational logic, and hopefully this will solve a problem. So the out should not be a register, it should just be an output. I can't do that here, so I should just generate it here. Hold on, let me go. I should generate this from my mind. Out is equal to... So first we check for func3. Func3 is 0. Then this is a question mark. Cool. So this one, we'd have another ternary. Here we do func7 is 0. If it is, then the output will be input... I should do this in parentheses. Input data A plus input data B, and I'll yoink that, and then I paste that in here, and obviously we need parentheses because of course we do, and this is going to be a nice minus. Cool. Then we know func3 is not 0, so here we do a nice func3 is 4, and then question mark, paste, oh, not paste. Here, paste, and we do the nice little caret, and then we deal with and or later. That's my current running thing I want to do. And obviously at the end we need a colon, all else fails, it's a 0. 13, invalid module instantiation. What is the problem with the output? We set it as the output, well, it's all good. It should all be good here. So let's hold on. Let's get rid of XOR real quick, and let's just go to the old state of this. That's just out. Syntax error. Input data A plus B. Hold on. What if I just always set out equals input data A plus input data B? Does it compile? Line 13 has an error. Okay, so there is. Oh, I forgot the keyword assign. Cool. So those are obviously failing because we're writing zeros. Here should be our XOR. So we should get 92. Oh, we're not doing XOR or AND yet. Okay, cool. Cool. So what we need here is we need to do XOR, right? So over here we do func3 is an XOR. We have a nice 4 for func3. 4 question mark. And then let me yoink that. And the caret. And colon 0. Cool. And so here 1 1 0 0 1 because this one has a 1 0 0. Yep, that is XOR. We can do XOR now. Cool. Finish. Then what we do here is func3. We set that as 6 question mark. So this one will be 0. And here this one is OR. Compiling 1. Cool. So we have the OR 1 1 0 1 1 1. Cool. There it is. And then now we add an AND. Colon question mark. Colon. Paste in there. And in here we do a nice func3 is 7 because 7 is for AND. And is 90. Oh, hold on. I forgot to change it to AND, I think. Yeah, I just did subtraction. Cool. So here we should have AND. Cool. 1 0 1 1. There we go. Cool. So we have our great numbers of we have XOR and XOR or an AND, which is a very nice sign. Very, very nice sign. Cool. Now, now you have to keep going. Make it, well, okay. We have these instructions. And hold on, this might actually be faster. So what if I have it... Hold on. So let me change this from binary, because I don't want to deal with binary here. I want it to be nice hex numbers. And from there, what I'm going to do is I'm going to delete this because I'm not going to be using that. Wires. Those are actual registers we have. And this should be on the positive edge. Cool. 0. Yes, that's correct. Why is this writing to x3? Oh, right. x1 plus x2 is x3. 61. 107, 153. Did sub fail? 153 minus... Wait, no, hold on. I'm printing out the instructions going on. I'm printing out the instruction. So, I'll go that far, and then add I x0, 15, x1. Yeah, I'll just put it at the end. Add I x0, 32, comma, x2. Add I x0, 11, x3. Add I... no, this isn't add, it's just add. Add x1, x2, x3. Let me just join, paste, delete. And there's x3, x1, x2. Let me just paste it in here, because this is just the general format for all of these, right? Delete, 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 delete. The bottom one could just safely be entirely dashes, so that's cool. I'm going to do that. Cool. And then here, add x3, x2 with x2. Then this is a sub. We're just going to go through here. Sub, x2, x1, x3. Then we do XOR, OR, and AND. XOR, OR, AND. And so these are x2, x1, x3. This one is x2, x1, and then this is x3. This way I actually know what's going on. Cool. So, when we do the sub, x2 minus x1, why are we writing to x3? Why is reg A 3? Huh? We're doing... So we're trying... It's thinking we're trying to do 15 minus 46, which is wrong. Huh? So let's figure this... Oh! Is it because add x2 itself doesn't work fully? Well, let's set time to be 2 here. Just make it go a little bit faster. Cool. So... Sub... So add, we have here. Sub, yeah, that's 92. So it's delayed by 1. Oh, that checks out, actually. That actually checks out, like, fully. Yeah, okay. Then we do XOR. Yeah, I trust it. Or an AND. Yeah, that checks out. It all checks out. Cool. Very fast CPU now. It's 1 clock cycle, 1 instruction. Now, CPI is now 1, guys. It went from 0.5 to 1 today. This is a great success. Amazing success. Yeah. Paste. And we move that to the top because that's a starting line. Cool, there we go. So that's empty, nothing happens. Then add 15, 32. Oh, it is 31. Yeah, it's not 32, it's 31. That's a printing error. That's because it's all ones and I... Whoopsies. Whoopsie-daisies. Cool. 15, 31, 11. Then we add those two to get to 46. 46 plus 15 is 61. 15... Oh, hold on. 61 plus 46 is 107. 107 minus 15 is 92. 15 XOR 107 is 100, which... I mean, the 6 we know is true, and then this one we know is going to be a 4 because F B. Or the OR here is going to just be 6F because that's the biggest one, and the smallest one here is just B. Yeah, that all checks out. This does, in fact, work very nicely. Yeah, that's actually very nice. That's very nice. Must be for... You know what? Do I want to work on sign extension? Maybe. I mean... Most significant bit extend. That's actually kind of annoying. Like, very annoying. Okay. You know, let's actually visualize our CPU. Let's visualize our CPU. Let's refresh this. And let's upload registers, ALU, CPU instruction decode. Open. Hey, nice. Here's our CPU. What? CPU? I just want to see a picture, please. Okay, let me, like, refresh this. I just want to see a picture of the CPU I built today. Open. CPU. Run. Okay, this is what we had last time. Cool. So, data W is a hex value. Out B. So this is a register. This is not a CPU. Can I see setup? Layout engine, simulation engine. There's a transform. Okay, let me throw in CPU TV on this. System task stop executed. I will comment that line out. Where is my CPU? Can I please have my CPUs, please? Click, 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 click. Click, not test bench. Okay, so we have that. We have all that. I/O. Set up. Why is it just going through our registers? I do not care. I want to go into the CPU. Hello? Hold on. Let me just pull in the CPU. Add file, cpu.v, open, run. Invalid cell type, ALU. So let's bring in our ALU.v. Now run. Invalid instruction decode. Now let's bring in instruction decode and registers. Now we run. Okay, it's just showing up on registers. It's not showing up anything else. This is kind of sad. Dang. Let's find out here. So. Come on. Online Verilog compiler. I just want to... I don't want to prompt. Shut up. Okay, this sucks. Any compiler that simulates it. Okay, hold on. NVim. SSH VVP. VVP help. Dash help. Cool. So what are we looking for? VVP just runs it. Okay. Hold on. NVim compile.sh. iverilog. iverilog help. iverilog -h. Cool. So there's iverilog-h. Brings to help interactive mode, VPI module, non-interactive. -n is exit. S is stop. Oh wait, no, it's here. What does this mean? Man, iverilog. Cool. So base C file, macro, dname. I don't really care. Which Verilog generation? I'm not doing anything fancy. Specify block support. G standard, G relative. It's extended types. Okay, whatever. It's a whole bunch of doubly do. It's path module n is debugging the compiler. -o is file name. P flag is value. Top module. Yes. Cool. And then T is the target. Verbose prints the version of the compiler. Runtime path. Your library's target. Oh, we can convert it to... Okay, that's cool, that's cool. Convert to FPGA. We can set it to VVP, which is what we're using. Warning types is all. Yeah, I don't particularly care. VPI modules. Whatever. Command files. Okay, hold on. iverilog. Create image of code. Okay, let's go into iverilog, and then that's all VVP. Hold on, iverilog usage. Okay, this is not. It's not going to work here, so I cannot see my beautiful CPU very easily, which is unfortunate. Yeah, unfortunate. Yeah, okay, hold on. Let's do the compile and run again. Nice, we have a very nice, beautiful instructions. I want full lines on them. So I want Vim CPU. Hold on. I just want a full line. I just want a full line. Yoink that. Paste. 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 We're just pasting. We're pasting now. Paste. paste, paste, paste. Cool. Compile and run. There we go. Nice and full line. I also probably want to add some new lines in there, but like whatever. I don't care that much, you know? Yeah. So we have the stuff going. It's clock goes on and then off, and then on and then off, and then when it's off, we change this, and it's very nice. Very nice, actually. Cool. So, what we need to do at this point is, yeah, we just have to, not here. All right, what do we want to do next? I don't want to do memory instructions. Those just seem hard because I have to implement memory, and that seems very difficult. Yeah. We could do branch. Okay. I probably do want to implement instruction memory at some point. That's just the thing I want to implement. We're going to do Harvard architecture. Well, caches and how they work is, you know, it's all Harvard architecture underneath, not von Neumann, but whatever. Whatever. We have this here. Yeah, so I want to do branch instructions. I want to, standard extensions, right. So you have multiply. Yeah, the atomic swap, add, and, or what? RD. Hold on, it's all format, the different opcode. RD is, oh, it's atomic, like, from memory. Okay, that's nonsense. Why would you do that? Multiply instructions, yep. Mul hot. That stuff's for 64-bit processes. We're not doing 64-bit processes yet. FD, floating point load word. No. Hold on, how are they describing load word here? Load word is just, yeah, okay, sure. Floating point load word, floating point multiplication, division. Okay, it's all just floating point ops here. Compressed. Oh, it's for, well, we're not doing compressed. Those are 16-bit instructions. And we're not doing any pseudo instructions because that's assembler nonsense. Okay, so let's look at the unprivileged instruction set. Let's pull it up here. Base instruction set. Cool. So we have that base ISA. We have formats, immediate encoding values. Yes. Cool. So honestly, I think this is actually a really nice place to leave it. So I will see you guys all later. Thank you for coming, one viewer, and see ya. Goodbye.